As we work more and more with derivatives, it's important to be able to tie them back to real-world statements. We'll start with something fairly straightforward to do with velocity. Simple statement like, I am walking at 1.2 meters per second. Based on that kind of statement, we can actually make predictions, and that's one of the major uses of derivatives. If we're walking at 1.2 meters per second, and we ask, well, how far will we travel in the next second? Well, I think we can all agree we would travel 1.2 meters, because every second, that's how far we're going. How about in 2 seconds? Well, I think most of us have the intuition that if we go for 2 seconds, we're going to go twice as far and get 2.4 meters. Of course, we can validate that a little bit more by saying we're taking our velocity times the time, and that's our 1.2 meters per second times 2 seconds. That's how we can get that 2.4 meters. Notice the units cancel out perfectly, and we get meters as the natural distance units. We can also extend that to smaller units of time, 1/3 of a second. So in that scenario, we expect the distance we would travel at a rate of 1.2 meters per second, but traveling only for 1/3 of a second, we would get 0.4 meters. Not too surprisingly, in less time we travel less far, and if we had to go up to something big like 10 minutes, the distance would be 1.2 meters per second, and then we just have to be careful. For unit conversions, I like the conversion of 60 seconds per minute. When we do that, we end up canceling the minutes, and we get the multiplier for the 60. So we're going 60 times as far times the 10 minutes times our speed per second, and we get 720 meters. All of these based on the simple derivative statement, velocity statement, that we're traveling at 1.2 meters per second. Now, something that's worth making explicit is that these are just estimates or predictions about what's going to happen. All we know is that now we are traveling at 1.2 meters per second. That's an instantaneous velocity, but we're basing our estimates or predictions on that. Take a moment to think about which of those predictions you think would be the most accurate. Going back a page, which of these 4 values would you have the most faith in? Based on an intuition, I think most people hone in on the shortest time interval. There's a reason for that. If we say we're walking at 1.2 meters per second, we don't know what the future is going to bring, but we know that there's going to be less change in the near term than there would be in a much longer term. I might stop walking, I might arrive at my destination after 10 minutes, but after 1/3 of a second of walking, I'm probably walking at pretty close to the same pace. So if we had to pick one, we would conclude that the smallest time interval leads to the greatest accuracy, or the most accuracy. All right. And that's based on a pretty natural assumption that on shorter time intervals, we're going to have less change, or less deviation, or less transformations from the information we're provided with about the current instant. Let's extend that to another kind of scenario, where we have a function that ties 2 variables together. So imagine we have a relationship between A, the amount we spend on advertising spending per month, and that'll be in thousands of dollars, and on the other side, the revenue, so how much money the company makes in that same time frame. Both are measured in thousands of dollars. So this would be an A value. So if you say we're at 200, and we're told that f prime of 200 is equal to 1.8. So I don't know where we are, but we do know that f prime, and this of course is a slope, is 1.8. So a bit steeper than 45 degrees. What does that mean in the context of our revenue? Well, it tells us, or a natural way to write out that interpretation, is if we increase A, then our revenue, or our function, increases. We can be very specific here. at 1.8 thousands of dollars. Put a dollar sign in front of there. Revenue per, that's a key phrase here, is the denominator, per 1,000 extra spent on advertising. So if we were to increase our spending by $1,000, we would expect to get $1.8 thousand back in increased revenue. But we'd also maintain that same ratio if we were to go for $2,000 in advertising. We'd expect that amount of revenue to increase by twice as much as that. Implicitly is also the backwards. If we were to decrease, we could replace this decrease with a decrease here as well, and that statement also be true. We tend to talk about things in terms of natural increase because that's the right direction when we talk about graphs like this. One little codicil on this is, if we talk about this rate of change, it's from a base of $200,000 of current spending, current advertising spending. That's where the 200 plays a role in this statement. Let's look at those statements more explicitly. If we were spending $200,000 in advertising and we increase that spend by $2,000, or increase it by 2 in the units we're using, then how would we expect our revenue to change? Well, we would expect, based on the earlier statement, that our revenue would increase by 1.8 thousands of revenue per thousands of advertising, and multiply by $2,000 in advertising, we would expect to get a revenue increase of $3.6 thousand revenue. Now, what about $1 million increasing in our advertising spend, or 1,000 thousands? Then the same model would predict that for every extra $1,000 we put in advertising, we get 1.8 thousands in revenue, and that would be 1.8. Oops, that would be 1,800 thousands, or 1.8 million increase in revenue. Now, it's important to note that this seems suspect. And why is it suspect? Well, because of the big change. This is a large change in A. We started off spending $200,000. Now we're going to spend actually 5 times or 6 times that total by the time we're done. That is a massive change. Going back to our graph, we would be moving from this point to a point way out here. There's no reason we'd expect the slope to be the same. So again, we can use these models to predict, but we get more and more suspicious about the quality of those predictions the further we get away from the value that we started at. Just as an understanding point, what if we had a slightly different version? What if we were told that this derivative relationship had a value of 0.8? Now, what that would mean is that increasing our advertising leads to increase of 0.8 thousand revenue, $1,000 in revenue for each 1,000 extra spent on advertising. And if that's the case, in principle, that sounds good. I spend more money on advertising, but I get more revenue. For those in the commerce econ side, though, you should be seeing something a little suspicious. What we're doing here is we're spending $1,000, and what we get back is 0.8 thousand, or we get back $800. That doesn't seem so helpful. So in fact, in that scenario, we should actually decrease our advertising spending. because increasing it is going to end up losing us $200. Every 1,000 we spend, we only get 800 of that back. We get some back. It's not completely wasted, but we don't make as much back as we're spending. So that indicates that we should go the other direction and cut our ad budget a little bit. Last but not least, let's take a look at an example more from the science side. Imagine a chemical reaction consumes reactant at a rate given by F of C, and that F value would be in moles per second. So F of C is already a rate. And the C value that it depends on is the amount of catalyst that is present. So think about that for a moment and think specifically about what the units of this derivative would be. F is the rate of a reaction and C is the amount of catalyst. Let's take a look. I find it very helpful to sketch a graph. Even if we don't have that much information, we know the relationship between the input variable and the output variable. We know that moles per second are the units on this side. We know that milligrams are the units on this side. So if we talk about F prime of C, what we're going to be talking about is a slope. And if it's a slope, it's going to be in moles per second per milligram. Let's take a quick scan over here. That would simplify here to moles per second milligram. And that looks like an awkward unit, but if we say it in a sentence, it's much easier, especially if we frame it out as the moles per second. So the moles per second tells us how quick the reaction is and how much that's going to change as we increase the number of milligrams of catalyst. Let's get more specific and look at a statement like this. If we have F prime of 10 is equal to negative 0.2, which of these statements captures that mathematical expression most closely? Let's take a look. The easy part is recognizing that the input here is C, so we're talking about 10 milligrams of catalyst. Notice that's our reference point for all these statements, so that doesn't help too much. The negative 0.2 is if we increase the catalyst, we see a decrease, because the slope is negative, of 0.2 moles per second, that's the units of F, per milligram of C added, or of our catalyst added. So when we see a derivative is negative 0.2, the value we're looking at, moles per second, is going to decrease as we add more catalyst. When that says we're not going to be speeding up the reaction, if we add more catalyst, it definitely will slow down the reaction. That is going to be true. However, it also turns out that we can invert that relationship. If adding catalyst makes the reaction slower, then removing catalyst will make the reaction faster, at least for small changes. And we're going to look at the mathematics behind that statement moving forward. For now, we're aiming mostly for an intuitive understanding or translation of these statements into words that we can then work with to make predictions about the system we're looking at.